This is question 6. A conical body rotates at a constant angular velocity in RPM in a container shown in the figure. So a uniform gap H between the cone and the container is filled with oil that has a specific dynamic viscosity, which is mu here. So determine the torque required to rotate the cone. So this is the cone, the rotating cone. So it is different with previous question. In previous question, we are using rotating cylinder. Now we are using rotating cone. And then for this situation, again, you need to draw the velocity distribution very well. So means that for this one, you need to understand that if we have 2 points, one point at the top and one point at the bottom here, these 2 points is actually not similar because point at the top here will rotate long distance here, while the bottom point here will rotate in a short distance. So if the distance is short, we know that F is equal to tau A. So means that the area here is shorter. So means that the force that need to rotate this one is actually smaller compared to the total force that need to rotate for this point. So means that in this situation we have two variables. So one is actually the value of R here. So means that the difference of radius here will make us we need to do the integral process to solve this problem because the radius here is different from one point to another. So and then before we solve this problem, I would like to draw a few diagrams for our assumption. So first is this diagram. So this diagram, let's say we have a triangular the cone shape here, and then we have the top point here, which is the maximum value of R, and then we have a small r here showing the various value of radius. So and then we assume that the distance from this point, so this is the value of x, so and then this is the value of L. Okay, if you could see, the value of L here is actually showing the capital R, means it's only occur at the maximum radius. So and then for small r, so this is the component of radius, so it's occur for the value of x. So and then we need to understand that because the travel distance for top and, let's say, for top and bottom point here is different, so we need to calculate start with a small area for each point. So let's say we are focusing into this point. So let's say we are focusing into this area. So we assume that the axis of x here is similar of this thickness because the inclination, okay, we assume that the inclination is very small, so we assume that the distance of this one is also equal to the x, mean a small portion in x direction. So and then this is the gap between these two moving and fixed surface, so it is equal to h here. So and then to simplify our calculation, we need to calculate, for example, if we take this ring outside, so it's occur like this one. So let's say we have a ring here, okay, so it's occur like a ring like this one. So and then if we cut this circular ring, so it can be expand like this one, so it is equal to the very thin rectangular area. So to calculate the area of this one, so it is equal to the length of this one So the length of this means the circumference of the ring. So it is equal to 2 pi r. So and then the height of this one, so it is equal to dx. So it is equal to dx. So means that we could calculate the value of dA here. So we could calculate the value of dA here. It is equal to 2 pi r times dx. Okay. So and then we have three basic equation. Torque is equal F times R, F is equal to tau A, and tau is equal to mu du over dy. So and then here we substitute the equation. So we have dq is equal to df dr. So and then we substitute the value of f here. So it's become tau dA and dr. So and then we rearrange the equation. So it's become tau r and dA. So and then we substitute the value of a here with tau r 2 pi r dx. So the value of a here is mentioned in this one. So and then we have a problem here because in this equation we need to integrate this equation to dx. However, if we look into our mechanism here, the difference is actually the value of r. So means that we need to change the value of dx here with dr. So how to change this one? So we refer to the previous calculation that we did. So we have this kind of drawing. So based on this drawing, we could say that the ratio of capital R over L, it is equal to the ratio of R over X. So and then we could write dx is equal to L over R times dr. So and then we substitute this value into this one. So we could get that okay, so we continue our calculation. So we substitute the du with r omega to change the linear velocity into the rotational speed, and then the dy here is the gap, so we substitute with h. So and then we get this term. So and then now we need to replace the dx here. So we replace with dx equal L over R dr. So in this calculation, so I just use the capital L here, okay, to differentiate in our calculation. So and then in this situation, please bear in mind that the small r here is not equal to capital R, because if you see the diagram, the r here is actually represent any value of variable r in the axis, but the capital R here is showing the maximum value of radius. So means that in this calculation, please make sure that you really understand all the parameter that you write to solve this one. So since the small r is not equal to r, so we need to write this equation like this one. So and then we need to integrate both sides. So we could write like this one. So integration of dq will give us q here. So and then the integration of r cube dr here will give us and the limit is 0 to r, because capital R is the maximum value. So we could get this term, and we have a constant here. So the integration constant need to be solved. So we assume that at r equal to 0, mean if at this point, mean at r equal to 0, there are no torque, because at this point, so the radius is 0, so there are no torque. So means that the value of c is now equal to 0. So and then we could rearrange the equation like this one, and finally we could simplify it, and we could draw the torque for rotating cone. So this is the rotating cone. Okay, can be simplified with this equation, which is Q is equal to mu omega pi LR cube over 2H.